not StatCrunch. If I go to, well, what I'm looking for is table, but I don't know if they have it here or not. Did anybody find the tables? So we're going to talk about test statistics. You noticed here you've got 8.4. Do you see where it says sigma is known? It's on 8.4. And, that's not usually the case. Sigma is what's reserved for the God arena. But 8.5, is more like what we're used to doing. So it's actually testing. It's using S instead of sigma, okay? That's the only difference. Okay, well, we'll start with this. What the heck? Does it go there? No. Right there. Okay, so these are test statistics. So you're going to set up your null hypothesis, and then you're going to decide, are you doing a proportion? What is a proportion? A proportion is just a percentage of your sample. Like, what percentage of the population has Tay-Sachs, for example? That's a Ashkenazi Jewish disease that's horrific. It's something like the blood cells warp, and it's a genetic mutation of there's a lot of genetic problems with the Ashkenazi in general, and a lot of it has to do with they were living in Russia and different parts of Europe, and they were always isolated. So there was a lot of incest, or cousins marrying cousins, right? And when you do that, when you have somebody has the same error term in their DNA and they hook up and have kids with somebody who has the same error terms, then the likelihood that, you have to go through a lot of genetic testing if you're marrying Ashkenazi to an Ashkenazi. So anyway, you're going to have to take this. These are your test statistics. So once you decide, this obviously is for proportion, right? So p hat is the percentage that you came up in your sample. Do you remember this? Okay, you're going to have a percentage, and this is what you're hypothesizing. This is your forecast. Statistics, the art of forecasting. And this NP, remember, that was a success and a failure, and it was divided by n, okay? Now, this right here is a test statistic formula. So here's if you're testing about the mean. Here's x bar. Here's p hat. See the same thing? X bar p hat against what we theorize is going to be the null hypothesis or the alternative. And here against what, this is when we're making hypothesis about the mean. Got it? Okay, so this is with sigma is known, right? And this is simply replacing sigma with S. And standard deviation is different than these because it's using a chi-square distribution. Okay, but this is what kind of chi-square distribution is what you'll do to chase hypothesis about deviation. Okay, now
is a chi-square chart or graph kind of like having an extended tail to one side?
well, yeah, you can again, you can do whether you want to. It's how you set up the null hypothesis and the alternative. If you if it's one tail, two tail, it works the same way. But chi-square can be a two tail. This thing in the book that you probably don't have has the normal, it has the t distribution, student t, and it has the chi-square. And on the first page, you're going to see your test statistics, right? Which is exactly these. Okay, so what do we use a test statistic for? What are we testing? Yeah, and what does the test statistic allow us to make a decision as to what? Yeah, and if it lands in a certain region, we call it the acceptance region, right? And if it lands out in the tails, it's a rejection of the null hypothesis. Okay, so it takes a little practice, but these are what you're going to be using in your final. You will be calculating if it doesn't tell you explicitly what the test what they are. Okay, so it'll be set up so you can solve for these. Okay, so in addition to that, we have the confidence intervals. Okay, now we can set up a confidence interval with a certain degree of confidence, and then we can calculate the test statistic. Now, keep this in mind. When we do a test statistic, okay, the area to the right or to the left of that is what? What is the area under the curve from the test statistic on out?
That's everything that it applies to.
Well, that's hard to argue with that one, yeah. Yeah, well, reject zone. What we call it, the area under the curve from the test statistic, depending where it's on the left or right, that area under the curve to the infinite part of the tail is called the p-value.
Oh, okay, sorry.
That is the p-value. The area under the curve from the test statistic is the p-value. Okay? So there are two ways to test this hypothesis, right? One's going to be the p-value. Well, we calculate our test statistic and we calculate how much area is to the right, right? And if that is bigger area, if that area is bigger than alpha, which comes from our confidence intervals, right? If it's a bigger area, then we're accepting. So let's draw a little here. Let's do it again. Okay. I was solving the equation. This is, I don't know if I told you, but this was the equation for a mortgage. This is how you pay. Yeah, this is the principal, the interest, the number of payments. This is how big a payment you're going to be. You can solve this for any one of these things. It's just financial. It's called financial math. And this is called a geometric sequence. So someday. But for now, I'll just delete it. Okay, so again, let's start this a little more detailed then. So I'm going to have my population, which you've seen this 100 times. Dang it. It's not calibrated right. Come on. What's wrong with this thing?
I think you still have it on the pen.
Okay. Let's see. Get that. Let me make this bigger. All right. So let's go back to the. Now, what I want to do is. Try that again. This corner here is where I messed up, because. Okay. All right. So, this is population. That's better. The population is everything, and we have these things called parameters. You better know parameters. And one of the main parameters is mu, which we call our mean, population mean, right? And then we have sigma, which is our population deviation. And this is our population. I'm just putting pop mean. Okay, then we have something called p, which is, I call it a little p, and that's our the true population proportion. Now, proportion, I mean really a fraction or a percentage. So when you're asking what percentage of the population has Tay-Sachs or sickle cell, from a collection of people, like right now, they are actually providing a vaccine to malaria in Mali and to children, and it's about 30% effective. I mean, but that's still a lot of lives saved that they're doing now. Of course, there's a lot of statistical analysis going on. If you want a field that's interesting and pays really well, right now it's called biostatistics. Okay, now we also have a true distribution. And normally we say that only God knows this stuff. It's a huge population of whatever observations. So like something that's sensible, something that's scientific in method, is that we take a sample from this thing, right? And we do this population mean. We do the sample. We can call it a sample space. Okay, and then we have X bar, which is from our data. That's our average that we're going to use to make boundaries on predictions and hypothesis testing about mu. If you recall that when we have a test statistic, right, when we're looking for a normal test statistic, the word test, remember what it was equal to? It was equal to X bar, yeah, which is what we generated, minus what we theorize this to be. Okay. Is that me? All right. Well, we have to hear it. Now, this depends whether you know sigma or not. So, if we know what it is, then we'll use it. But normally, you would use S. Okay, so one of the test statistics was just S divided by the square root of 9. So just S in there and put the square root of 9. And, I mean, where this is little n for the sample size, and this is capital N. I know you've seen this at least 10 times because I've done it 10 times. And this is going to be S, which is the sample, right? It's a sample deviation. And that's going to be used to make predictions about the true population, yes? And I ask you this in a question, and I want arrows. I want arrows from here, this direction. I don't want pointing back, because that's not the way we're going. We're using this to make inferences about that. And this is going to be, what do we call this P here? It's like this P, but what's the difference? This comes from our sample, right? It's like what percentage have Tay-Sachs, what percentage are midgets, what percentage. Anytime you're asking not the mean, but a proportion, then we have P hat. We took it from our sample. Out of so many, we're midgets divided by how many sample size n. You can't test about mu anymore. We're testing about the true proportion. Does everybody know what I'm talking about? Is it okay? Or no? Does anybody ever understand what a proportion is? It's simply a percentage, or if you want to look at it the most basic, a proportion is a ratio of so many to so many. Okay, so this is our test statistic. Now, usually we use depends on how it's structured. We can use a binomial, or we can use a normal distribution or we can even use a t distribution if some of these are known or not known. Okay, so now we have, these are all test statistics for one population. So we do the same thing, see? What we do now we have a test statistic that we can call it whatever we're using here, I don't know. So I'm going to have I don't know what you want, a p-test. And that's going to be, p hat minus the p, you see? That's a lot like this. See it? It's the difference between the empirical measurement and the theoretical thing that you're trying to forecast, divided by the square root of P, which, remember, is a success and Q is a failure. So this can be either a t-test or a binomial test. So I'm going to say this p-test can either be used, you can use a binomial distribution, which is there's a table for that, or if the sample size is large enough for certain things, then you can just use the normal curve. And you use the normal curve if you know what sigma is, right? But you can use the t distribution, you know, if you're using S instead. So now we have 3 test statistics. Guess what? P hat's going to be the best forecasting of the proportion, the true P, right? And finally, we have the histogram of the data to kind of give us an idea what kind of process to be an estimate of the true distribution. Now, is there anybody that does not understand my sketch? Ask me now, because you can't really do chapter 8 without some kind of foundational thing, which I started from the first day of the class. It should start to making more sense. Now, let's talk about the hypothesis testing itself. When you do the hypothesis testing, there you can use a test statistic, and you want to see if this test statistics, once you choose your level of significance, this area under here, let's say you're doing a two-tailed test, this is the probability of like a type 1 error. So the tighter this is, the less chance you're going to be making a mistake, but it's going to take more processing power. So this area, okay, so this area here, if it's two-tail, which you can tell by your alternate hypothesis. Remember, your null hypothesis is always going to be something equals. The other one is going to be pretty much what you want to show that the dude's lying. So if he says more, you're going to say less. Or if he says it's just different, then you can do two-tail. Okay? So the type tail test is going to decide. So if I tell you that alpha, right, if alpha is equal to, let's say, I don't know, let's say the confidence interval. We expect that to cover 95% of the experiments, right? So that 1 minus that gives us alpha. Okay, so now, if I take 1 minus alpha, so I actually divide that by 2, right? So I have 0.0025. That's area under the curve. That's not this value. It's not this critical value. And this one's also 0.00, you know, then we have the 25, right? Okay, so what I want you to know is that this number is alpha divided by 2. And what is alpha? Alpha is equal to 1 minus whatever confidence interval you check. If it's 95, 1 minus 0.95 gives me 0.05. If we have it set up as a two-tail, then we split that alpha into 0.025 and 0.025. Okay, now, once that's set, okay, we can check now, depending on which test statistic, and see where it lands. So that this area will be, we fail to reject, you know, we accept if you want, okay? And this would be, if your test statistic hit over here in the red, then there's not sufficient evidence to support the null. But the alternative, do you see what I'm saying? Okay, go ahead.
So if it's in the green, you fail to reject it, you have significant evidence?
Yeah.
Okay. But if it's in the red, you fail to reject because there's
You reject the null.
Yeah, reject it. Okay.
You reject the null. There's not sufficient evidence to reject a null. That's a safer way of saying it. Okay. Now, that was testing your hypothesis. This is test with the test statistic. Okay, that's one way. The other way is once you got your test statistic, yes, and let's say it hits, I don't know, let's say this time the test statistic hit right here. Okay, let's say it was the Z test statistic, yeah? It hits right here. Okay, so one way we can do it is just look where the test statistic hits. The other one is to calculate this value. The area from here over is what? What's that called?
Wait, the area
From the green.
isn't that your critical?
The critical value is here.
Okay.
Critical values are determined by this alpha. P what? P value. The area is called the P value. Okay, if this area is greater than alpha divided by 2, you can see you're in the acceptance area. So when you do your midterm, you'll be able to show me a test statistic and where it hits. You'll be able to do a confidence interval, and you will be able to calculate from the test statistic the p-value to determine whether, so we can either use the p-value method or the test statistic method. Okay, it'll make a lot more sense, I think, as you get more and more practice with the homework. But really, that's what the whole course is about. Now, let's do a quick refresher on the confidence intervals. So, with the confidence intervals, let's just start over. Okay, so confidence interval is a probability. See, this is confusing because there's a p, but that means probability of bracket, right? And now, if you want to talk about mu, and what we would like to put a boundary, right, on this. And in any case, what we're bounding with is something we calculated from this man's sample size, right? Which is, what's the best predictor of it? X bar. Do you see it? Now, on here, we're going to have an error term, right? And here we're going to have Z sub alpha divided by 2. Yeah? And we have this error term, and then over here we're going to have, that's Z plus this error term, and this is going to be minus Z sub alpha divided by 2 times the error term. Okay, and then we decide what kind of, here's your confidence interval. If I say 95.95, that's my confidence interval. Notice the connection over to alpha, because alpha is equal to 1 minus the confidence interval, see? So there's a tie-in in that way. And we see that these are the Z values on the curve. So when we have our curve like this, and we have this alpha divided by 2 here, and an alpha divided by 2 here, yes? These critical values are Z critical values. This is the minus version of that, okay? So these get in here. So if we have 0.25, we have to go in the guts of the table and find out what our Z-score is, remember? You go in the guts of the table and you find out, well, we'll do some. And you'll find out what their Z-score is, okay? So the confidence interval is really telling us what kind of range we need, in order to, so every time we run the experiment, we expect that 95% of the time that interval that comes out fits within this term, okay? Now, that's okay. That's our error term now. Do we have the same idea? Well, why not? If we're talking about proportion, right? Again, there's that true P, true proportion, right? And what do we use to bind it with? No, I'm not. That was mean. Okay, so I used X bar to bound. So what binds?
Oh, that's P naught.
P hat.
Or P hat, right?
Yeah. So we have P hat, right? And then, right? And then we have plus. And then now we'll have some calculation now, depending whether you're using binomial or you're using the normal distribution or the t distribution. So, so we have, this plus some error term and p hat minus the error term. Okay, and we can do that. I just want you to see that it's the same kind of reasoning that we're binding, putting limits onto God's truth with a certain confidence interval. And because this is connected to the alpha, it's setting up our acceptance zone and our rejection zone. Okay? Now, so could we have the same one? Yeah, we could have one like this. Suppose I have, now I want to put boundary around sigma. So then I go like this and like this. And then that's going to be bound by what?
That's going to be bound by your sample. It's going to be by
Sample deviation.
Yes,
there we go.
sample deviation. And in that case, it has its own distribution. So we're going to bind it by n minus 1. N minus 1, right? And there's the S. And then we're going to divide that by the test statistic, or the left and right. So we're going to have the chi-squared right on this one. And then we use the chi-squared. That's the left side. Okay, and over here we have n minus 1 sigma. And over here we'll have chi-squared. This is the left side, this is the right side. Okay. We'll try some of those so that it makes more sense. So, no. Are we okay? These, again, would be, I could do it like this, put it in a big bracket, put the probability, and then put the confidence interval here. Okay, now, the only thing else is that, you have to know which distribution you want. So, okay. Let's look at the problems, I guess. Any questions? If you have the confidence interval down and you have the hypothesis testing down and you have the p-value down, I think you're down. You're down with the hood. You'd be a down. You'd be down. That's what they do in prison. Okay, they'd be down. They'd be tripping. Okay, no tripping. Now, let's get rid of this. Let's see if we can get some good old, let's see. Okay, let's see what I put there. Did I put final or midterm? Yeah, practice final. Mostly A. Yeah. Well, you can actually, I have it posted as one of your assignments, right? Or this is just a PDF file. Okay, so this will be your final, right? It'll be a lot like this, except there'll be certain numbers changed a little bit to protect the innocent, So let's look at this problem to begin with. It says, the blank is the value used to make a decision about the null hypothesis by converting the sample statistic score, right, with the assumption that the null hypothesis is true. So, anybody know, this is what we call our test statistic. It's our test statistic, right? That's what's determining whether we're accepting or rejecting. I'm not sure how they have it like that, but that's the same thing. It's see it. I guess I don't know why. Maybe it's repeated. I don't know. Test statistic goes there, yes, or they want you to mark this. Okay. Now, which is not true when testing claims about the proportion? These are not always the same. The conclusion based on a confidence interval estimate will be the same as conclusion based on the hypothesis test. Not necessarily. So, this one's D. Look and read some of these. When testing claims about the population proportion, the traditional method and the p-value method are equivalent in that they yield the same result. Okay, that's true. But this is looking for not true. So you see how the problems are set up, so a lot of them you don't have to do a lot of extensive calculations, but you may have to calculate some test scores. Let's see. What does I already finished? What I thought I only did 2. Oh, there's 3. Okay, that's 5. So, okay, 3. I don't know how I missed that. Okay, so I was already here, right? So 3's right here. Okay, I had marked D here. Remember? Okay, now find the p-value. So we're going to look for the p-value. Okay. And it's telling you that the claim for a smartphone carrier data speed was 17 megabytes, right, with a sample size of n, of 19, yeah? And it's giving you a test statistic. And what test statistic is that? This is a T test certificate. So you already know that it's going to be asking us about, let's see. It's going to be asking, this test, the t-test statistic will be equal to, the p, what we got, p minus p hat, or, so, well, the true p, right? So we have p hat minus what we think it is. That's the null hypothesis. That's the forecast, right? Divided by PQ, or Q is equal to 1 minus what we theorize P to be. And then this is the square root of n. Okay. Now, so this is our test statistic. What is our p-value? Now that we have the test statistic, okay, how do we calculate our p-value? Now that we have a test statistic.
Just get p-value on one side and everything else to the left.
Well, the idea is that if you have, a t distribution looks a lot like a bell curve. It's a little wider. But if I have a test statistic that hits here, this t-test, okay, this area over here is the p-value. So what is this asking you to do? Well, it already gives you the t-value, so you know where this hits, right? What I want to know is the area from here over, and that would answer your p-value. Are we okay with this? So there is a, if you're going to use a table, there is a t-distribution, and you're going to use degrees of freedom, which will be 1 less than the total sample size. So if you go down to the table, A3, and you will see that you have 18, right? And then you go over to as close to the test statistic as you can get. Now, if you do this on StatCrunch, it'll give you a lot more accurate. But you can see here, if you look on, well, I don't know if you have access to the table or not. Probably not. Let's see. Well, let's take a look. Let's find one. Let's see. Let's hear. Let's do let's try, we want the student T distribution table. Okay. So I was going to 18, right, because the sample size was 19, right? And if you look at your test statistic, the test statistic was given to be 2 point something. That was 2.584. Okay, so if I'm 18, there's 2.55. See it? And then this depends whether you got a one tail or two tail. That would be how much area is under the curve. So we have 2.552. So it's going to be close to 0.01 and a little bit more. Do you see that? That would be a one tail to the right. That would be determined on the hypothesis test. So now that we got our idea, it's when you do it on StatCrunch, you'll get a lot more approximate number if you're going to do it on StatCrunch. I don't need that. And it's just okay. So roughly, that's your p-value. Yeah, right there. So I calculate this right here, and this p-value in here is this guy, or something a little bit bigger. I think it's 0.019. Oops, that guy. And so that is your p-value. Okay. Compare that with your alpha, you know, whatever confidence interval you wanted, and that's why you can accept or reject accordingly. Okay, so first, they're telling you, they did this calculation in this problem that we're doing. We're already, okay, so, here we have, okay, we already did that. That was D. And then I'm having trouble. Okay, there's 3. Okay, now, there's where you put in your p-value. Okay, so it's the area, depending, so there's a p-value. I think it was like, what did I say is point? Yeah, so that's going to be 0.01. I think it's 9 is closer. Let me see. That's number, yeah, it's 0.019. If you are proficient on your T-Crunch, you can put these in and it'll give you the p-value. Any questions? Does everybody know what a p-value is? I mean, you have to be clear in your mind the difference between your level of confidence, your alpha, and your p-value, and your test statistic. Okay. Let's go on. Okay, here we have the standard deviation now. Read this, because our test now is about the standard deviation, which uses a chi-square distribution. Okay, so here we have a pulse rate was about 11 beats per minute. that's the deviation, right? That's the deviation from the mean. That's not the mean. It's the deviation. And there's the random sample of 139, yeah? And then that has a standard deviation of 11.7. Okay, so now we need to complete part A and B. So this one here is going to be, if you're going to talk about express the claim in symbolic, so we would have a null, right? I don't know if I got that. So we could call that a null. Yeah, so 5, number 1, we'll put express the real claims and sigma. So we want to say sigma, right? That's what we're talking about. Equals. Okay, now what do you think we put as what we're testing? Well, this would be, okay, this is going to be 11.7. Now, do we want to show if it's greater than in the alternative or less than? So let's see, we want to, in this case, more than. See, that says more than 11. So we could look at this instead as this. That would be, our null would be that equals that. Right? So actually here it is. So the null would be that sigma is equal to 11, yeah? And the null hypothesis, right, will be that sigma, and this time I'm going to put less than 11. 11.7. Yeah. You see it? So you see my null? Okay. And then so now we're going to use S. Remember in the chi-square distribution. And then I'm not sure what this means here. Let's see. Number 1. Oh, that's number 1. Okay, so number 5 would have been what we're testing is this guy. See it? Because we're talking about the deviation this time. And we picked that one as our null. Alternative. Now, if we look at that and then we say, okay, are we okay with that? Looked like it was bleeding. Okay, we go here. This is, which of the following is not required for testing a claim about standard deviation? What is not required? Well, let's see. This is used, the chi-square distribution. Must the population be skewed to the right? I don't think so. So this is the only one that is not a requirement. Oh, this one. Okay. Well, that's easy enough. Oh, let's look at this chi-square business there. Well, we can do one of these. So the chi-square distribution also has degrees of freedom, and it looks a lot like the this t distribution. I'll pull it up because you have area to the right of the critical value, and that's how it's adding up. So let's see if we can set one of these up. I already did that one. Let's see if it's got another one, because we didn't actually do a chi-square. Let's see if we have it here. So that was number 6. Okay, so where's 7? Oh, look, I got the part of the table here. 16. Okay. I have the answers there as well. What happened? I got 6. I'm missing 7. 10. Well, let's see what we're talking about. So 12 different video games showing alcohol use was observed. The duration time of alcohol use were recorded with times in seconds listed below. Assume that these samples data, here's your significance level. That is alpha. Is a test of the claim that the population mean, so we're talking about, right, the mean, greater than 80 seconds. If you want to construct a confidence interval to be used for testing that claim, what confidence level should be used for a confidence interval? If the confidence interval is found to be from here to here, do you see? It's giving you from negative 44.2 seconds, bounding God's truth, with 2.65 on the right. And what should we conclude about the claim? So the confidence interval, right, would have been like 99%. And notice that now I'm assuming we're doing a one tail here, but 1 minus 0.99, the 0.01. So that is our confidence interval. So we have this guy set up like it is. So we have the confidence interval P is going to be, and it tells us minus 44.2 less than mu, less than 255.4 seconds. Close the thing, and then put equals. And then remember what our confidence interval is, 0.99. So what can we say about that? So we came up with, let's see, so here's the mean of, is it greater than 80 seconds? Well, it's certainly in there, right, in the range. So what should we conclude about the claim? The confidence interval 1, the value of 80 seconds, so there is or isn't enough to, well, it does contain it, doesn't it? Yeah. And then is it sufficient? That, I'm not sure. Is that sufficient? No, I don't think so, but let's check. So that's number 10. That one is, oh, I need the right problem. 5, 6, 7, 8, 9. Okay, so it's, and it is not. So this one is going to be, it does contain, but it is not sufficient. So we haven't used either a p-value or a test statistic, right? But we did look to see if that thing was contained within this. It does. See, that's why it's not exactly, why a confidence interval is not exactly telling you the same thing as whether you accept or reject the null hypothesis, which was on problem number 1.
So whenever I answer these questions, I always have a hard time figuring out
Yeah, you want to see a test statistic, see where that hits. You want to see the p-value as it relates to this 0.01, which is your alpha. But the problems are set up pretty good. I mean, you could put these numbers in if you want to actually calculate a particular p-value or confidence interval where they gave it to you, or you can use calculate a test statistic, a t-test statistic. Okay? All right, let's see what we can do with this other one. Okay, so here, Erickson's method of one variable method claimed to increase the likelihood of a baby girl in clinical trials. Result could be analyzed with a formal hypothesis test and an alternative hypothesis test of p. So we're talking about the true proportion. We're saying that is greater than 0.05, which corresponds to the claim that the method increases the likelihood of having a girl so that the proportion of girls greater than 0.5. You would have interest in establishing the success of the method. Which of the following p-values would you prefer? Well, if the p-value is very small, that means your test statistic is hitting at the extremes, right? If it's getting bigger, this is bigger, that's a lot smaller. And then 0.5, 0.05. Okay, so could formal hypothesis, the alternative hypothesis is, that's the alternative, is p is less than 0.5. So the hypothesis, so it says the hypothesis method 3 is or is not effective. And this one is it the null, or supports or rejects the null? So on that one, they're picking on number 11. So they're saying you're going to pick, this is extremely small, 0.001, 0.001. And then, now, this is really, really small, right? So you would expect it to support or not the null hypothesis.
You think it would support?
Okay, so let's see. So let's say I have something like this, and I have here. Okay, and now I know that this area is 0.001, which is quite small. So if the test statistic lands on this side, you would accept, right? So,
So you would accept?
well, yeah, because, the test statistic looks to me like it's going to hit to the left. So that would be an accept of what? Well, what is our null hypothesis? Actually, this is actually the smallest of all of them, isn't it? Yeah. So this is the tightest as far as the smallest alpha that we have. Okay? So, so it is. Now, on the alternative was this. Right? And so, in essence, we're accepting that there's no difference, or there is a difference, because it's hitting over here. Okay? And it says it strongly supports the null or the alternative. Well, the null is how we set up the thing. So we got a p-value of 0.001, yeah, and then it supports the null or the alternative. Now that's the tricky part here. It says so we have the results could be analyzed testing the alternative hypothesis. So we're testing to see if p is greater than 50%. which supports the claim that the method increases the likelihood of having a girl. So that the proportion of girls is greater than 0.5. If you have an interest in establishing the success of the method, then which of the would you use? Well, this is the tightest. That's the lowest type 1 error. And it says, so this says it's accepting. So we're accepting evidence as to the null. The null is that it's equal to 50. So yeah. So I think it's the alternative here. So we'll set that up in a second. Here we go again. Critical value of a drug intended to help people stop smoking. There were 129 subjects were treated with a drug for 12 weeks. This is at biostatistics. 11 subjects experienced abdominal pain. If someone claims that more than 8% of the drug users experience abdominal pain, is supported with the hypothesis test to conduct at the 0.05 significant level, using 0.19 as an alternative value for P. The power of the test is 0.96. Interpret this value of the power of the test. Okay, so this is 0.96. And the chance of rejecting, that's the chance of rejecting would be your 4%, right? Number 12. So we have 96. Okay, so we have the null. So when the true is actually, so P is equal to, they tell us what P is, right? 0.5? And when the proportion is actually, well, what did we get from our thing? Did we get 8%? Oh no, I'm the wrong problem. Let me go back. Okay, start over. Okay, so now we have 129 subjects were treated for 12 weeks. 11 experienced abdominal pain. So would you agree this is a proportion, yeah? So the proportion is going to be the p hat will be equal to what? 11 over whatever that, yeah, whatever that is.
129 is the total subjects.
There's a 4% chance of rejecting the null hypothesis with a p-value equal to what? Well, the p-value we're saying is 8%, right? And the actual true proportion that we calculated from our sample is what? What's 11 divided by 129? Okay. All right. And now we have, so let's see how I got it here. This is on your, your course, your Canvas. I mean, it's in my math lab. So when you do these problems, it'll be easier than what I'm doing. I just made a copy here. So for number 12, then let's see. We have the null. We have 0.9. We have 2 is greater. The proportions who this is supposed to be greater. Okay. Okay, so so here we had 4%. That's the the power shows that there is a 4% of rejecting the null. 4%. All right, and the p-value, I already put it in. I thought I put it in. You told me, was it 0.08 something?
0.08.
Okay, and then, but it's the hypothesis of p, and the actual came out to be, what was it? 0.08. Okay. So, let's take a look at that now. That's your proportion, 0.8. This is what the data showed on the sample. And then the proportion of users who experienced pain is greater, right, than 0.08. So the null hypothesis, the alternative hypothesis they call it, says the proportion. Okay, so the alternative, the null, oh, well, that's what I did here. The null is greater. Okay. See, this went from number 12, well, 15. Okay, so the test statistic, they're giving you the test statistics already. 2.83 is obtained when testing the claim that p is less than. So this is like an alternative. The alternative, if they do it that way, would be that p is less than 0.74, right, where we would have our null, where p is equal to 0.74. Okay, so we want a significance level of 0.10, right? So we need to find the critical value for that. And should we reject the null or should we fail to reject the null? So first we have to do is clear this up. Okay, so what are the critical values? Well, if you notice, we're doing a one-tailed test to the left. So if I do a one-tailed test to the left, then over here, right, I'm going to put in how much they want my alpha. So I know what this is, right? Yeah. Well, now I have to find this z critical value. Notice the z critical value is not the z test statistic. Okay, so if I go into the guts of my bell curve, and it's filling up from left to right, and I'm going to go to a 0.01. So 0.01, no, is it 0.01? Oh, it's okay, 0.01. 0.01. Okay, I got, let's see, so you have to look at the guts of the table, right? So now I have to look for,
Wouldn't it be a negative though?
yeah. Oh, the z-score will be negative. But I have to figure it out. But it's filling up, the chart is filling up from left to right. So I have to look in the guts for, basically I'm looking for 0.01.
I think it's actually,
So if, here it is here, I got 0.001. No, I want 0.01. 0.03, 0.01, 0.0107. I got like 2.3, minus 2.3. Oh, they gave us a test statistic. See it? But that's hitting over here. Minus 2.83. So if that test statistic is here, it's hitting in the reject zone, right? This is our critical value. This is our alpha. But they already tell us the test statistic. The test statistic is this area on back. You can see it's sitting to the left of the critical value. Correct? So, so we reject the null, not sufficient evidence to support that. Well, that is our alternative. And then fail to reject null, not sufficient evidence to support. What is the difference? Okay, fail to reject. Instead of saying reject, they fail to reject. But we're in the rejection. So, so we reject a null, and right, and there's sufficient evidence to support the claim. Because we're rejecting the null. And the null is that P is equaled, okay, we failed on, we didn't reject that, right? We rejected the null, correct? And say there's sufficient evidence to support the alternative. Any questions? That would be number 15. Any questions? Okay.
Yeah, is our final going to be on my stat level, or are we coming in for it?
Coming in.
Okay.
That's one thing I promised them I wouldn't do a final online. Okay, so that's. Yeah, I think so. I think that'll be okay. The problem with using the computer is that I'm surprised how many answers are there to questions. It's amazing. Because they have this quiz thing, like, I don't know. I mean, I've seen people type in the actual questions and the answers already posted on this quiz. And I can't believe they'd have every version of it. But anyway, what the heck? Go ahead.